Hi, today we're going to go over the Inferential Statistics Report. This is Project Part 3, and I've already posted an example of having this report completely filled out, and I'm just going to run through it in this video as well, so you can kind of hear me talk through completing each of these parts. So we're going to go through each of the comparison questions, all four, and then we'll go through the regression question. Comparison number one, we're comparing a mean or a proportion to a value. And my first example is going to be comparing a mean to a value. And here's the question that I was answering. To answer this question, is the mean age of participants more than 35? We're going to use a hypothesis test where we compare a mean to a fixed value. So step one, the null hypothesis is that the mean mu is equal to 35, and the alternate hypothesis is that the mean is greater than 35, and I'm choosing greater than because of what is written in the question. That more than is going with the alternate hypothesis of greater than. The second step is the test statistic. We're going to use a t because I have unknown population standard deviation. So t is going to be equal to x bar minus mu sub 0 over sample standard deviation s divided by the square root n. Filling those values in, my sample mean was 41.0, rounding to one decimal place. I subtract 35, which is that value of mu from the hypotheses, divided it by my sample standard deviation was 14.4, divided by the square root of the sample size, which is 58. Okay, plugging that in my calculator, I get test statistic of 3.173. All right, to get the p-value, we are going to use the online p-value calculator. There's a link to this under the Project Part 3 section on Foxtail. All right, once we go to that tool, we're going to fill in the t-score. We fill in the degrees of freedom, which is one less than the sample mean for this kind of test. And we can fill in the significance level, it's 0.05. This is a one-tailed test. We look at the alternate hypothesis because it's just more than, it's one-tailed. And we calculate, and that gives us a p-value of 0.001216. Okay, so step 4, we're going to compare that p-value to our significance level, which you can choose whichever significance level you want. You can default to 0.05, which that's what we're using for alpha. We see that our p-value is less than that significance level of 0.05. It'd also be less than 0.01 if we were to choose that more conservative significance level. So for our conclusion, we are going to reject the null hypothesis. So the next thing is to describe what this conclusion means in the context of the topic. And because we have rejected the null hypothesis, which says that the mean is equal to 35 years of age, we can conclude that the mean age of participants is more than 35. Finally, you want to give some indication as to how you calculated your values, either by calculator or maybe you used a spreadsheet, Excel or Google Sheets, to do the calculations for you. Either way, circle or underline whichever way you calculated your results. All right, now this is a look at comparison number 2, where we are comparing means of two variables from one single population. The comparison that I'm making asks the question, is the transition time from swim to bike the same as from bike to run? So transition time 1 compared to transition time 2. So first step is hypotheses. The null hypothesis, always something about equality. So we are wanting to know, is the mean difference between those two times equal to 0? There's no difference. And the alternate is that the mean difference is not equal to 0. Because it asks the same as, we want to flip that and be not the same as, which would be not equal to. It doesn't say anything about greater than or less than. And because we're using a not equals there, it is a two-tailed test. For the test statistic, this is where we find the differences in between the sample values for each of the sample members. So I'm going to take the difference between transition time 1 from swim to bike and transition time 2, bike to run, for each of the sample members, and then find the mean difference and the standard deviation of the difference. And then the test statistic is t equal to that sample mean difference minus mu sub 0, which is equal to 0, and then divided by the sample standard deviation of the differences over the square root of the sample size. We can replace mu sub 0 with 0 and then plug the values for x part of the differences and s of the differences. All right, and here are those statistics. You can see these if you want to reference back to my sample data and descriptive spreadsheet. You'll see how I calculated these values. All right, so let's plug these into our test statistic. So we are going to get the sample mean difference is 107.9. We're subtracting 0, so we don't have to actually subtract anything. Divide by the square root of the differences, 116.5. And then divide that by the square root of the sample size of 58. And these times that I am using here, the unit is seconds, in case you're wondering. All right, so if we calculate that, we are going to get a value for the test statistic of 7.054. P-value, we're going to use that online calculator where we plug in that test statistic and the sample, or the degrees of freedom, which is 57. Also, we want to indicate on the calculator that this is a two-tailed test. So it's a really small p-value. P-value is so small they don't actually give it to us, but they tell us it's less than 0.00001. For our conclusion, we can see that that is less than any of the significance levels that we might choose, 0.05 or 0.01, and our conclusion will be to reject the null. So the conclusion of the test in context of the topic is that the transition times are not the same. Our null hypothesis was that they were the same, and we rejected that. So we conclude the opposite of that they're the same and to say that they're not the same. The next comparison is comparing the mean of one variable from two subpopulations. The comparison I'm making is expressed with the question, is the average bike time for the 40 to 44 age group the same as the 45 to 49 age group? So the two subpopulations are the two age groups, and the variable is the bike time. So look at the hypotheses. The null hypothesis is that the difference between the means for the two populations is equal to 0, that there is no difference. And for these purposes, we can use the 40 to 41 to be the group that's expressed by mu sub 1, and 45 to 49 would be the group that's expressed by the mu sub 2. The alternate hypothesis is going to reflect what is asked in the question. It is saying the same as. So we want to say that this difference is not the same. In other words, the difference is not equal to 0. That makes this a two-tailed test. Here is the test statistic calculation and also the sample statistics that are from my data and descriptive statistics spreadsheet. So we're going to plug things in here. So x bar 1 minus x bar 2, we have 48.2 minus 52.5. And then we subtract the difference between the mean values, which that's 0. That's coming from right here. That's divided by the square root of the standard deviation, 7.8 squared over sample size, so that's 9, plus now for the second sample, standard deviation 8.7, square that over the sample size of 7. That results in a test statistic of negative 1.026. To find the p-value, we're going to need to determine the degrees of freedom. And this is a complicated calculation, which I have not asked you to learn how to plug into your calculator. So we use the online tool for this. All right, there's a link for this on Foxtail. And we plug in the sample sizes, we plug in the standard deviations. We're going to then just compute the degrees of freedom. We get 12.2549, and remember that we are going to round that down. So we get degrees of freedom equal to 12. Now we will use the online calculator to find the p-value, plug in the test statistic, that degrees of freedom, select that it's a two-tailed test, and that's going to give us a p-value of 0.32513. And because that is greater than our significance level of 0.05, we are going to not reject the null hypothesis. And the conclusion of the test in the context of the topic is that the mean bite time for the two age groups is the same. We did not reject the null hypothesis, which says that there is no difference between the mean bite time for these two age groups. So we can conclude that the bite time is the same. Comparison number 4 is comparing two proportions, and the question that gives this comparison is the proportion finishing in more than 2 hours less for the 30 to 39 age group than for the 50 to 59 age group. Writing down the hypotheses, the null is always that there is no difference, so we are going to take the difference between the proportion of the first population minus the proportion of the second population and say that that is 0, where we use 30 to 39 as group 1, and 50 to 59 as group 2. The alternate is going to be about the difference of those two proportions, but it is going to reflect what the comparison is asking, and it wants to find out if the proportion is less for the 30 to 39 age group. So if this proportion P1 is less than P2, this difference is going to be less than 0. It's going to be negative. And that makes this a left-tailed test. Okay, we want to calculate the test statistic, and I'm giving us here my sample results and then also just a reminder of what the formulas are. First, we calculate PC, where we add together the counts that correspond to each of our groups, and it's not listed in my data table over there, but it's 2 for the group 30 to 39 and 4 for the group 50 to 59 over the total sample size for each of those groups, which is 8 for both of them. So we end up with 6 over 16, and that rounding to 2 decimal places is going to be 0.38 for PC. So we can now calculate the Z test statistic. Our sample proportions, P prime, A and B, which we're calling P prime 1 and 2, we'll subtract those. So from the table, we're using these values. It's a proportion greater than 2 hours, so 0.25 minus 0.50. And then we subtract the difference between the values in the null. So this is 0, so that's why we subtract that 0. Divide that by our PC value, 0.38, times 1 minus that, which is 0.62, times 1 over the sample size from the first sample, plus 1 over the sample size from the second sample. They just happen to be the same. That's not always the case. It's okay if they're different. That results in a test statistic of negative 1.030. To calculate the p-value, we're going to use the online tool for finding the p-value for a Z test statistic. Again, there's a link on Foxtail for this. Plugging in that Z-score of 1.030, I'm realizing I didn't put the negative in there, which it actually is not going to matter, but let's see, where's my negative? There we go. And the other thing is we want to indicate this is a one-tailed hypothesis test, and then we calculate, and that's going to give us a p-value of 0.151505. Comparing that to our significance level of 0.05, we see that our p-value is greater than our significance level, 0.05, so we are going to not reject the null hypothesis. So our conclusion in the context of the topic is that there is not sufficient evidence to conclude that the proportion finishing in more than 2 hours is different. We did not reject the null. The null was that they were the same, that there was no difference in the proportion finishing in more than 2 hours. So we conclude that there is no difference. Okay, finally the relationship question where we perform linear regression. The relationship that is being tested is there a linear relationship between the variables of age and overall place for women? And I see that I misspelled overall, so let's plug in another L there. What is the correlation coefficient to 2 decimal places? The R that is calculated, and these were all done using Excel, which I'm going to refer you to the other video that is posted for Project 3, where I go through how to calculate R and the intercept and slope for the linear regression equation using a spreadsheet. So R from my spreadsheet is 0.43, and because it is positive, it is indicating a positive correlation. We don't yet know if it's a significant linear positive correlation. That'll come when we do the hypothesis test, which is next. So we're going to use a hypothesis test to determine if there is significant linear correlation, and if so, at what significance level. So the null hypothesis for testing linear correlation is always rho equals 0. So that's not a p, it's a Greek letter rho. And if it's 0, that means there is no correlation, no linear correlation. And the alternate is always that rho is not equal to 0, which means that there is correlation. There is linear correlation. The test statistic is calculated as R times the square root of the sample size minus 2 divided by the square root of 1 minus R squared. So plugging things in, we're going to get 0.46 times the square root of n for my sample is 58, so n minus 2 is 56. And then that's over the square root of 1 minus 0.46 squared. Just a note, if you get a negative R, you want to make sure when you square that, it makes it positive, because that squaring applies to the number and the negative, which is going to make it positive. Calculate that value, it's 3.564. To find the p-value, use the online calculator for a t-value, and remember that the degrees of freedom for this test is n minus 2. Because we have 2 variables, we subtract 2 degrees of freedom. So our degrees of freedom will be 56. P-value that we get from the online tool is 0.000755. For our conclusion, because that value is less than 0.05 or any significance level that we would use, we are going to reject the null. When we reject the null, that means we conclude that there is linear correlation. Next thing is to write the equation of the regression line. That's always going to be y hat, and then we want the intercept. This is calculated using the spreadsheet. So check out that video again to find the formula or the function to use to calculate that. It is 8.6 for my example, and then plus the slope times x. So my slope is 0.51. So there is the equation of the regression line. For my example, x, the independent variable, is age, and y, the dependent variable, is overall place in the triathlon. Next question asks about the slope of the regression line and explanation of what it means. The slope is 0.51, which that means that for every increase in the independent variable, which in this case is age, there's going to be an increase equal to the slope. So the place, the overall place, will increase by 0.51 for every increase in 1 year of age. Part C asks about the intercept. The intercept is 8.6, which means if the independent variable is 0, if x is equal to 0, then that's what the independent variable or the dependent variable would be. So if age were 0, then the overall place would be 8.6. Now that would mean that age was equal to 0, and that doesn't make sense in the context of the results of a triathlon. So even though this is a mathematically correct value for the equation, it doesn't have any practical meaning because 0 is not in the original set of data values that were used to calculate the slope and the intercept. Finally, r squared. R squared is the coefficient of determination, and we get that by squaring the correlation coefficient, in which this case is 0.43. Again, if you have a negative r, you want to make sure that you square the negative so it ends up being positive. So 0.43 squared, we get 0.1849, which we're going to round that and make it a percentage, so that's 18%. The interpretation of r squared, the coefficient of determination, is that 18% of the variation in the place that we see in the results is explained by its relationship between age and place.